one connection point to the shield at the bottom of your equipment, of your building. It has the surge protection for the power, for the data line, because the power is going into the outside world. The data lines are going into the outside world. Current from the lightning will flow into the ground and pollute this power through transfer impedance. There will be a common mode current over the power. You get a differential mode current voltage in return on the power, a spike. So you need spike protection here in the bottom of your building. That you connect to the lightning protection. This is the lightning system outside. It's sort of cage outside the building. These conductors are lightning. And you keep an isolation up there. Usually that doesn't work. For real buildings, there's always something there. A chimney or whatever with big contacts, so you have a problem there. Some of the lightning current will then go through the inner workings. And then it might still work if you make it nice and white metal and low impedance. But okay. But this is the idea. The ideal for lightning protection, that you have a lightning protecting conductor system on the outside. The inside is isolated up there, only connected here, and there's a surge protection on any wire going outside, like, again, current bar. And then if you have the lightning current, it might still be working afterwards. It will flow on the outside, and here it will flow in the ground, but anything made here will be short-circuited here, so that you can work safely inside. ESD. Oh yeah. Oh, you know it. Good. So no secrets here. Yeah. This is the long version. That's a nice lady. Well, essentially, it's a big car and a small lady that plays some role here. No, it's still okay. No problem. So now we're going to the tricky part. It sits there. You see, carefully comes out, not touching anything. And that's the fault. Now she touched something. Oh. Had she touched the door, or whatever, that's no problem. You should not do this.
Blijf kijken ook.
You better leave it inside because it will go on by itself. Like this. You get a big fire. Okay, I have an experiment here. If you want to get it on camera, you have to come close. Okay, this is plastic sheet on aluminium bottom. I can rub it. I will charge. I didn't have a little heat. Metal plate. So this is the first activity. Rub it with some different material. from the plastic. Then put the sheet on metal plate. Put it on like this. By rubbing it, you get a negative charge in the plastic plate. You put anything there, print the circuit board, well, I have one here. Well, I have a complete disk drive, but okay. Metal plate will also work, so what happens is that the negative charge will push the electrons away, because it's also negative charge. They go to the top side of this plate. The plus will be on the bottom. And the next step is you discharge this plate by touching it to the bottom plate. So there, there's a finger coming, boom. Okay? So I connect it here to the bottom plate. And then what happens is that by discharging it, only the negative charge will go away. The plus charge is still against this negative charge on the bottom. So then if you lift it, you can make sparks. You can hear them and you can make them even audible on the radio. If we have a quiet spot on the radio. Not so quiet. The noisy building. Everything. Each machine. You can see little sparks here. Well, that's difficult for you. Okay, so what I did, I put a light here, a little neon bulb, and there's a metal bar here going from here to here. So it's a U-shaped metal, and I disconnect a discharge on this screw here going through, connecting it to this side. So actually I'll discharge through this metal plate, and then you see the neon light go on, which means that there's at least 90 volts over this hairpin type metal. Now the point is, how can we get it to see it? Sometimes difficult. Very first connection is usually the heaviest. Yeah, you see that we have light out. Well, very little. Yeah, you can see. So 90 volts. That means that it's a very fast current. The IDT, because to make 90 volts over this hairpin here, which is about 20 nanohenries or so, very small inductance. To make 90 volts there, you need a large DIDT. And that's, yeah, this experiment you can use to show the effect of ESD. Now, if you put anything there, probably still won't work, but we can try. That's the idea with electronics. The electronics, you have a charged surface like a table. You put the electronics there, isolated fashion, and then you touch them. You get this charge transfer, this shift of charge, you touch it, and then you get a discharge. At that moment you will destroy your electronics. And then if you lift it, the voltage will go up. That's this law. The voltage is the charge divided by the capacitance. If you keep the charge the same when you lift it, the capacitance goes down, so the voltage goes up. And then you get bigger sparks. You can exercise that in the winter, next few months. If you walk in the corridor, you charge, and you meet a friend, you give a hand. If you lift 1 foot, it's twice the voltage.